Good afternoon, ladies and gentlemen. I try to be short. I know that it's a hard time after lunch, but I try to be at least a little interesting for avoid. So for a start and hit the spirit, let's start thinking about two interesting sentences about the concrete in the world. The first one, it says around 70.5 cubic kilometers of concrete are made each year. That is more than 1 cubic meter for every person on Earth. It was said by a Geological Survey of USA. The second one is that concrete is used more than any other man-made material in the world. So what's the reason for this large use of concrete? There are many reasons, but I try to put here the main reasons. The first one is its capacity of support, high charge of solicitation, of course the high durability, resistance, the flowability behavior for filling, forming work, and in addition is relatively economic material for use in construction. So once see the famous or the successful of use of conventional concrete, the non-conventional concrete showed up for try to achieve the expectation of the new construction, try to achieve the demand of technology by covering new necessities, make easier the execution process, that is decreasing cost of time, opening architecture design possibilities, include ecological aspects, of course, and give answer to designers and other professionals. All of them is valid if at the same time you can be compatible all the time to traditional performance required by regulation like safety, durability, and so on. So these papers will focus on the some of non-conventional concrete were included in some regulation like the Spanish Structural Code and the EN 206 that are self-compacting concrete, fiber reinforced concrete, lightweight concrete aggregate, and recycled concrete aggregate. So I took just to put shortly, briefly, some aspects of each concrete. First of all, the soft compact concrete is very well known by the most of people, but do you know that it was developed in Japan in '88? It was recognized as a new revolutionary development in concrete sector. The main characteristic, as you well know, is the flowing ability to accommodate by its own weight without external energy, and of cohesion to maintain an homogeneous mix without segregation. But it's important to take into account some aspects really required by some regulation. One of them is the correct selection of material, of course. The quality production control is really important in this kind of concrete. After some scientists' study, it was found that the performance of this concrete is really comparable to conventional one. The benefits are many, but some of them are faster construction, best finish, energy reduction to place cement because you don't need the external energy, improve the durability in some case, and reduce the environment impact because it's the consequence of the rest of benefits. The Spanish experience, you can talk about many experience, but some of them is, for example, the Institute of Arts and Contemporary Culture in Tenerife, or the Water Tower built in Zaragoza in 2008. Talking about the fiber reinforced concrete, it was started in 1920 with glass fibers, and then in 1960 was started the use of other type of fibers like steel and others. It's commonly applied in elements like slab-on-grade architecture, concrete structural elements, because its benefits to some aspect of concrete, as you say before. But important aspect you have to take into account is that the aggregate proportion is our essential information for select the fibers. In each case, it's important to consider the fiber length in relation to the maximum diameter of aggregate. The homogeneity of concrete mix should be controlled all the time. The suitable consistency of concrete is important when you use the fiber, because the uniformity is an important criterion. And in Spain, the Spanish code required that fiber should be less than 1.5% in volume for structural application. The benefits of concrete are many, like improved properties of hardening concrete, like strength, ductility, durability, and so on, and also against action during the surface life, like resistance against abrasion or avoid cracks and so on. Also, I'd like to talk about the experience in Spain is, for example, the build of this bridge in Zaragoza. It seems like a fish thanks by the glass fibers. This aspect is because the glass fibers, the bright and so on. Also, the lightweight concrete aggregates is a typology also used at European international level. It started in 17 in USA, believe it or not, for the construction of warships. The common type of light aggregate is expanded shale, clay, or steel materials. But it's important to consider in the design of concrete that aggregate absorption rates can modify the requirement of water cement ration, and of course can be consequence of consistency. It's important to take into account in the design. The benefits in concrete is, for example, it's suitable for rehabilitation of existing structures. The decreasing dead load has the consequence of the decreasing cost of slab on grade, for example. Is able to achieve similar strengths and other properties like a concrete when we can use normal weight aggregate, providing lower thermal conductivity and increase the insulation properties of building. It's also really important properties. In Spain, the experience is mainly in precast industry for constructing, for producing walls and other insulation elements. But I can mention two of singular structures. For example, the Picasso Tower in a famous avenue in Madrid. It was built some elements with lightweight aggregates. And also the Guggenheim Museum, some part of them was also built with lightweight aggregates. The last one, typology of recycled concrete aggregates, which also included in a Spanish structural code. Nowadays is a used typology in the most parts of Europe, but it's important taking account some aspects in the design. For example, the quality of recycled aggregates depends too much on the origin of these recycled aggregates. It's important to eliminate other material which could be contaminate these recycled aggregates. One important point is in Spain, the Spanish structural code permits the use of this type of aggregates in structural elements. But it's important to limit the percent of substitution. In this case, it's 20%, but you can use it in structural elements also. Benefits, of course, eliminates the needs of disposal of wastes. It protects the natural resources. Experience in Spain. In Valencia, it was built in the last year the first bridge built with recycled aggregates in the world. In Spain, it's also used for non-structural use, like fill natural soil in excavation and pavement base. But instead, in the Spanish structural code, it's not included the use of fine parts of recycled aggregates. We use in Spain for this type of elements, non-structural elements, this part of the recycled aggregates, which usually is eliminated of this volume. This all type of non-conventional concretes can be overlapping, feasible, and you can put in addition some properties like colors with pigments, also the properties of self-cleaning concrete or different special texture. But for try to be more interesting, the use of non-conventional concrete, it's interesting to mention other type of concrete maybe would be showed up in the future. For example, the concrete with optical fiber, you can see in the photo, in the picture, or concrete made with beer and sugar, when you have as answer some herbs and so else, and concrete with magnetic aggregates inside, as you can see in this picture, an example. So, once you say everything, you can emphasize the suitability benefits of concrete. You can start with this sentence. It was said in Johannesburg in 2002, the suitability in building construction can be understood to something which goes well beyond simple environment protection. That is, natural material is not synonymous of sustainable material. It's more than this. You can ensure the contribution of overall life cycle, reducing the cost by a good insulation properties, or increasing the thermal, decrease the thermal conductivity, increase the comfort of users. And concrete can contribute in many manners to this objective. So, as conclusion, you can see that it's completely possible to select the most suitable concrete from a sustainable point of view, mainly use the non-conventional concrete. The comparison between non-conventional and conventional concrete should be based on a long-term, and as I said, and a performance-oriented criterion. So, advances in concrete science and technology can positively contribute to improve construction industry sustainability. So, thank you for your attention.
Thank you very much, Renata, as well. It was a very interesting lecture and a very good overview. I have only one association, because you were speaking about the lightweight aggregate with the LCA. Yeah. Coincidentally, this also the life cycle analysis, the abbreviation. Maybe this is a next job.
Yes.
Thank you very much once more.
Thank you very much.
And I apologize that we can't have a discussion now, but we hope at the end we will have some time. And we go to the next paper, which is the paper 123, Building with Earth, a sustainable material for efficient buildings. It's a paper which is made by 3 colleagues, but it will be presented by Liuzzi Stefania, yes, or correct. Stefania Liuzzi.
It's the same as
it's
you
the
want.
same? Please, the floor is to you.
Thank you. The paper that I'm going to show you is named Building with Art, a Sustainable Material for Efficient Buildings, and I want to show you in a brief introduction the meaning of unbaked earth, which means the raw material extracted at least at 50 centimeters from the arable land, which includes clay, lime, sand, and gravel without the organic matter. The production process for the end building product is made by natural driving without firing in the brick kiln. As you can see in this picture, the material is totally recyclable after the disposal, and you can make a lot of products like mortar, plasters, and bricks. The aim of the work is was to assess the agrothermal behavior of a small building by comparing 3 different cases, like 3 walls: fired clay, concrete, and the unbaked earth wall. The tools that we used are the best test building, that it is a benchmark extracted from the International Energy Agency, the software for the simulation that was Energy Plus, and the last one was the A10 master transfer model extracted by Kunsel, and so it uses the transfer and master transfer equation. About the building material data, we consider different properties about the physical properties and the thermophysical properties. As you can see, about the unbaked earth, we measured in our laboratory by a lot of specimens of different sizes the vapor diffusion resistance in a climatic chamber and the dry thermal conductivity by using an isomet apparatus according to the UNESO norm. About the other building material data, as you can see, there are the agrothermal properties, that is to say the absorption curves, and we compare 2 different materials, the unbaked earth and in particular the fired clay. And you can see from these graphics that the absorption coefficient about the unbaked earth in green is better than the fired clay ones. And so you have the possibility by using this material to absorb and dissolve the relative humidity, the moisture content in a room when the relative humidity changes. About the climatic context, we choose a Mediterranean climate context, that is to say, the city is named Bari, and we consider in particular some summer months and some winter months in which you can find some temperature and relative humidity values very particular. Other boundaries conditions were the classroom, in which we supposed 12 people. The occupation time was supposed between 10 a.m. until 5 p.m. and the moisture generation rate was supposed 1994 grams per hour. The air infiltration rate was supposed constant all day, about 0.5 hour up -1, and we considered that there weren't any conditioning or heating system in the room over the furniture. We want to assess in particular the moisture buffering capacity, as you can see by this definition extracted from Rode and Grau. And about this, we considered the relative humidity value, in particular in the summer of July, in which we can find a very high relative humidity and temperature value. By a comparison between fired clay and unbaked earth wall, and in particular unbaked earth is exposed in red and the fired clay is exposed in yellow arrow, you notice that by using an unbaked earth wall, we can achieve a better damping of the indoor RH fluctuation. And the other consideration, the other remark that is important to say is that the use of unbaked earth can allow us to achieve a constant value of relative humidity value in an average range between 50 and 70%. Another remark is about the air vapor pressure in the months of October, and as you can see by the comparison between fired clay in yellow and unbaked earth in red, you can notice that it is possible by using unbaked earth achieve a lower moisture air content, and another comparison is possible between the unbaked earth without any other layer and the unbaked earth with a very thin layer of water vapor barrier. And in this case, by this comparison, we can achieve a lower vapor pressure value, as you can see from the graphics. Another consideration is about the comfort conditioning and the comfort indoor conditions, and about this we have taken into account the daily frequency of relative humidity value on the inner north surface. In the red box, you can see that the unbaked earth can allow us to achieve a relative humidity value between 60 and 70% for about 14 hours a day. And the best remark that we can say is that the relative humidity value goes over 70% for on the average 2 hours a day. And this is the best remark that we can say. About a comparison between a concrete wall in blue and a concrete wall covered by an earthen panel, the thickness of the wall is the same because it's 35 centimeter. We can notice that we can achieve by using an unbaked earth a significant indoor comfort improvement over damping relative humidity fluctuations. And over this, we also taken into account the thermal performances, and about this we compared the building material, that is to say fired clay wall and unbaked earth, and we can see from the graphics that the two lines are the same, are very, very similar. So the two buildings materials show similar indoor temperature values. About the results, we compared 3 different cases, as you can see from the presentation, but we can notice that by using unbaked earth, we can achieve a better moisture buffering performance over a similar thermal performance in terms of thermal conductivity and transmittance compared with the fire clay instance. So that is to say that we can have a better indoor comfort with the lowest environmental and economical cost. Briefly, let me show you the different line of researches that are ongoing researches. The one is carrying on by the Polytechnique, the University Polytechnique di Bari, in which we prepared a lot of specimens of different size about lightweight earth, that is to say earth with straw, and in particular barley straw, and stabilized earth, that is to say earth with lime as a stabilizer. We are going to measure some important physical, dry density, thermal conductivity, and so on, and microscopic properties by a lot of equipments. And the other line of research that we are going to carry on is in collaboration with the University of Nottingham, and in particular with the Department of Mechanical and Material Structures, in which we are studying the stabilized properties of query fines earth with the addition of different percentages of lime, and in which we are considering the mineralogy and the internal structure with the different technique of scannings like SEM, BGH, and BAT. And the main aim of this work is to relate these properties in regard to the internal structure with the hygrothermal behavior of the material themselves in order to obtain a sustainable material. I want to thank you for your attention.
And we thank you, Stefania, very much. I am living in a refurbished mud house with half-meter thick mud walls, yes. And I did not know what you told already before. It was very valuable for me as well. Thank you very much.
Thank you very much.
So our next paper is 127. And it deals with the development of thermal insulation materials from the beginnings to the appearance of the plastic forms. And it will be presented by David Bozaki. David, the floor is yours.
Good afternoon. My name is David Bozaki, and I'm from Hungary. I'm a PhD student at the SCHMID University in the city of Győr, and I will talk about the development of thermal insulation materials from the beginnings to the appearance of plastic forms. Let's see the contents. After a short introduction, I will show you the development of the natural and the synthetic insulation materials, and then I will tell you what kind of changes came when the plastic foams appeared on the market of thermal insulation materials, and in the end I will give you a short conclusion or summary. So we could believe that the history of thermal insulation materials is a short history because long ago thermal insulation didn't form separated layer in the building construction, and there was no need to build extra materials to assure the insulating function. But we can think about that the cause of building activity was the protection against the elements, for example the cold winter and the heat of the summer, and also against the wild animals. So the main cause of building activity was the insulation. So this is why the insulation is as old as the building activity. In the beginning of the history, prehistoric people built firstly temporary buildings, and they used materials for clothing, for example animal skins and wool, vegetable materials, and later because of the settled lifestyle they needed durable materials like stone, wood and earth, and at this time the earth houses and cave dwellings were very popular too. The first insulating materials were certainly the natural materials, for example the vegetable fibers. For example, in hot climates people build their dwellings from dried eelgrass or straw or something else, and in hot and in cold climates the thatched houses were very popular from the 12th century, and these materials were the first materials from which people made the first insulating panels. The first panels made of reed and flax were very popular in the beginning of the 20th century, but their hygroscopic ability and flammability caused very big problems. The first products were the flax linium. It was made of flax, and the silotex, it was made of reed. They were spread at first in the USA. The dried eelgrass was also important insulation material that was used firstly by indigenous people by the Caribbean Sea, but the revival of this technology happened in 1893 when Samuel Cabot made the Cabot quilt. It was an insulation material from dried eelgrass. It was sandwiched between two layers of paper. The other important insulation material was the cork insulation. In the ancient times, Romans used it for roof insulation, and in the Middle Ages, in Spain and Portugal, it was used for wall insulation too. The first insulating panels of cork were made in the 1870s and 1880s. The straw bale construction also was a very important thermal insulation material. It was born in the 1880s in Nebraska State, USA, and a little bit later, in the 1940s, the compressed straw bale insulation was born in Sweden. The wood wool was first produced from the needles of the pine in 1842, and the inventor was inventor made blankets for it, and it became insulation material only in the beginning of the 20th century, when in 1908 the Heraclit company in Austria made the first insulating product from wood wool. The cellulose-based thermal insulations appeared in the 1920s in Scandinavia, and Also, in the middle of the 20th century, materials of animal origins became very popular. For example, insulating panels from sheep wool. And then came the synthetic materials. The first synthetic material for insulation was the asbestos. It was firstly used in Finland in 3000 BC for chinking wood houses. But the ancient Romans and Greeks used it in places that were exposed to fire or high temperature because of its fire resistance. In the industrial ages, it became very popular insulating materials. For example, it was good for pipe insulation or insulation of steam engines. But asbestos has a very bad harmful effect that was well known in the ancient times too, and the use of asbestos became forbidden in several countries of the world in the 20th century. Then another synthetic material was the mineral wool. The natural mineral wool was firstly used by inhabitants near volcanoes, for example in the Hawaii Islands. But the first commercial mineral wool product was made by an inventor called Edward Purry in Wales, and he made it in 1840. The slag wool was invented in 1885 in Manchester, UK, and the rock wool was invented by an American inventor, Charles Corridon Hall, in 1897 in Indiana State, USA. Fiberglass was well known by the Egyptians and Venetians. The glass makers used glass fibers for decorating their vessels, but the glass fibers, as seen as the silk fibers, was only invented by an American inventor, Edward Libby, in 1893, and the fiberglass insulation was invented by Russell James Slater in 1938. He was the owner of the Owens Corning Company in the USA. The foam glass insulation was patented firstly in the USA and in the USSR too in the 1930s, but there were no idea to use it for thermal insulation until the 1940s, when the first foam glass product was made by William Lytle, also in the USA, and the first insulating product of foam glass was produced in Pennsylvania State, USA in 1943. In the end of the 19th century, there was a goal for the brick maker companies to upgrade the thermal insulation ability of building bricks. And at this time, hollow bricks and ash-filled bricks appeared on the market. The first product was the Bischweiler's brick in the end of the 19th century. And in 1923, the aerated autoclaved concrete, AAC, joint blocks were invented in Sweden by Johan Axel Eriksson, and this is we know nowadays as Itong. It was also a good insulating product. The loose insulation were used also in the 19th century. The dross was the first from these materials, but in 1917 the expanded clay was invented, and in 1938 the expanded perlite, also in the USA, and it was used for aggregate, for example in concrete structures. So these were the synthetic materials, and then came the plastic foams to the market of thermal insulation materials. at first we must know that there are three methods to make plastics. The polymerization was the first that was first observed by Henri Regnault in 1838, and the first human-made polymerization was made by Charles Goodyear 1 year later. The polycondensation and polyaddition was invented a little bit later. The most important plastic foam insulations nowadays, the polystyrene and polyurethane. The natural polymerization of styrene was first observed by Eduard Simon in Germany, but the first synthetic styrene was invented by Hermann Mark. He was the worker of BASF company in Germany. And 1 year later happened the first successful polymerization of styrene by Karl Wolff and Eugen Dörrer. And another 1 year later, Munters and Tannberg patented the foam polystyrene. The first polystyrene foam was invented by Ray McIntyre in the USA. He was also a worker of the Dow Chemical Company, and this company made the first polystyrene foam product in 1943 under the name of Styrofoam. In 1950, the EPS, expanded polystyrene foam, was also invented in Germany, and the first product was named Styropor. It was produced firstly in 1951. To produce polyurethane, the polyaddition technology was invented in 1933 by Gibson and Fawcett in the United Kingdom, and the polyurethane was firstly produced by Otto Bayer in Leverkusen, Germany, and in 1954 the first commercial polyurethane product was put on the market. So, in the end, we can say that we cannot imagine our buildings nowadays without thermal insulation, because the high energy prices and some other things, for example, global warming, climate change, make us to use them in huge numbers. But if we take a look at the market of thermal insulation materials, we can see that 50 or 55% of these materials are mineral wool products, and 40-45% are the plastic foams, and only 5 or 10% of natural materials is used. And nowadays is a very urgent problem to grow the amount of natural materials because of the sustainable development. But unfortunately, these materials have very wrong disadvantages, for example, flammability or low durability and hazard of rodents and insects, and the advantages often stay in the background. For example, they are environmentally friendly or economical, ecological too, and they can be much more inexpensive than the other synthetic materials. Thank you for your attention.
David, köszönöm szépen. This was Hungarian because he comes from Hungary, so thank you very much. I only missed the term of Hungarocell. Do you not call it anymore in Hungary, the styropor Hungarocell?
Hungarocell was a name of a product.
Yeah. Okay. Yeah. It is funny that it was called like this.
Yes.
Thanks a lot.
Thank you.
Hopefully we have some time for discussion later. But we go to our next paper, and this is a paper made by a number of authors, 1, 2, 3, 4, 5. And our colleague Laminaga will present the influence of anchorage systems in flexural strengthening of low-performance concrete beams with basalt and steel textile reinforced mortar. It's not really a short title.
No.
So we are looking forward.
Okay.
The floor is yours.
Good afternoon to everybody. Thank you, Mr. Chairman, for the presentation. And okay, the title has been already read, so I will start directly. Before starting, I am going to show you a brief part of the experimental campaign I am developing for my PhD. But before that, I would like to make a brief introduction about the scope of our work, and which is this strengthening material we call textile reinforced mortar that you can maybe you saw in the morning with Professor Trentafilu. During this Congress, several people have spoken about the rehabilitation business, and it's clear that in Spain it's a very small part of the whole construction area or the whole construction business in Spain, only the 24%, while in European average is the 42%. This is our data from 2007. And there are some countries as Germany or United Kingdom which in this rate exceed the 60%. As you can see, the difference is very high. And now in Spain the situation is that the new construction is in crisis. So this opened a new market for this sector most in the southern countries of Europe. A good example is that the 60% of the housing estate built in the Basque Country, the place where I come from, is in the north of Spain with 2 million of inhabitants, need immediate rehabilitation. So with this data, it's easy to see how more or less how is the scope of our work. Among this rehabilitation, a lot is provoked by the bad quality of some concrete structures built during the first half of the last century. This pathologies has three main reasons. The first one is the lack of knowledge about the material. In the beginning, it was thought to be as durable as natural stone, which is not true. Another important thing is the inappropriate use of materials. In some seaside regions, as this one, Cantabria or Basque Country, it was very normal to use sand of the beach, which is very bad for the steel corrosion, and also applying steel and some materials that now they are forbidden. And the next point is the no specific standard. I want to remark that in Spain the first chapter of durability or quality was introduced in 1973, which we can see before that there was not any regulation about that. So in this project, compiling some information, we have defined some kind of concrete we call low performance, and more or less they have to fulfill these features that they give this condition of bad quality. I want to remark the low compressive strength, which is more or less related with the cement, high porosity, chloride content, which motivates the steel corrosion, the water-cement ratio, and the carbonation level, which gives the natural protection to the steel rebars. So in order to simulate this concrete, we have manufactured one concrete of our own, with more or less the rough features is 17 megapascal, this amount of cement and very high water cement ratio. And in order to simulate the steel corrosion, the amount of steel rebars is quite low. Among all the strengthening systems, in this case is flexural strengthening, we are working with textile reinforced mortar. This is a composite material which is the joint of cementitious matrix, a mortar matrix, and a textile fabric. This composite is different from the FRP. FRP is a solution very broadly used now, and it has some drawbacks like very bad behavior in high temperatures, and even is destroyed with a fire. A bad application in some surface, for example with a moist surface, and it's difficult to retire. It's a non-reversible solution. And besides that, there are different mechanisms for the FRP. The matrix has a lower strain than the epoxy resins, which is more or less the main used matrix for FRP. This provokes a better distribution for the forces, and the bond concrete mortar is lower than the organic adherence of the epoxy resins. The combination of all these properties is indicated for strengthening deformable structure, that are these low performance concretes. They have the problem with FRP that they are so stiff that sometimes there is a peel off of the strengthening material with a destroy of all the covering of the beam, in this case, or a slab, and it's a very irreversible damage. So the TRM materials are two, basalt and steel. The basalt is a bidirectional fabric, as you can see in the picture, and the steel is placed in a propylene net in order to be in the same direction all the time. And the difference between these two LD and MD is the density of the wire per centimeter. The medium density is 3 times more than the low density. In the table, it's possible to see the mechanical properties of these materials given by the manufacturer. And as mortar, we are using it's not a very sophisticated mortar. The content of polymers is less than 5% in order to be suitable for fire prevention, not to be destroyed. The Spanish standard say that it's necessary to be less than 5% of polymer in the mortar. And these are more or less the mechanic properties, no bigger than 20 because the concrete is 17, and a good flexural strength. Summarizing all this, we are looking for easy and cheap, easy to install, cheap and reversible solutions for these kinds of structures in order to increase the rehabilitation business in Spain. So the experimental campaign is focused in this presentation on third scale beams, 1.5 meters span, and it's a 4-point flexural test. Here is more or less the picture. We measure with LVDTs the span and some points. And in this table it's possible to see more or less the campaign. There are 20, as I said before, 2 of each combinations. And in basalt, it's divided in two stages. The first one is with no anchors. And in the second, we are going to see now the failure mechanisms. So in some situation, we use anchors in the ends of the strengthening system. And as you can see, we play with the number of layers, 2 of basalt to see the difference, and 3 of low density steel, because we want to see the same amount of medium density, but in this case the shape is different. So the penetration of the mortar in the low density is better than in the medium. So we wanted to check that. These 2 pictures summarize briefly the strengthening steps. The tensile surface is roughened and cleared in order to achieve a good bond between the strengthening solutions. Then it's moist, humidify the surface in order to achieve a better bond also. And as we can see, the first layer of mortar is spread in the tensile surface. Then the fibers, the textile fabrics are installed and covered with another mortar, a layer of mortar. In case of more layers, it's the same. A new fabric, a new sheet of the fabric, and covered with the mortar. And in the next sheet, it's possible to see the 3 failure mechanisms we have found in this experimental campaign. Firstly, the tear-in rupture. This is the best situation. It's a ductile rupture. The strengthening system is finished till the textile fabrics break because the strain. And these 2 are not non-desirable. Is the debonding at intermediate flexural crack, started in the middle, as you can see in the picture, in the lower picture. And the other is even worse, is the debonding at the outermost crack, and normally this happens very soon. In order to counteract these two bad results, 2 anchor device has been tested in this campaign. Firstly, the U-shape, you can see in the left side, is the same, is made with the same material, with mortar and the fibers. In this case, it's covering the tensile surface and also the sides of the beam, and steel plates bolted to the beam. And now I'm going to present very quickly the table. You can see better in the preceding book, but it's possible to see how the effect of the two basal layers is not very significant. But yes, the basalt, in this case with two layers, the debonding happened. So it's possible to see how these anchors improve also the ultimate moment and also the deflection on that moment. In the case of steel, the same with the two of anchors. A means the steel plates and U is the U shape, and you can compare with the third of the four how is improved the both things. And in the case of the three layers, logically is bigger. Now I'm going to show some plots. It's better than the tables. I only wanted to show how in this case with the anchors the deflection is improved even the double. And in this case are the plots, moment versus deflection of the mid-span. In the lower plot, the blue is with one layer and the red is with two. It's possible to see the difference. And of course the black one is the control one. And in the upper graphic is possible to see the effect of the anchors. It's not very significant. But here in the steel, yes. In the upper graphic, the blue is only one layer of the steel, of the low density steel fabric, and you can see how suddenly there is a decrease of the moment. It's because of the debonding. The red one in this case are the steel plates. You can see that the ductility of the beam is improved, and in this case it's more or less the similar. This is the U-shape anchors versus the steel plates. More or less the result is the same, but it's possible to see that the result is better and it's easier to install the U-shape than the steel plates. And finally, the medium density steel in the upper, the difference between the non-anchored beams versus the anchored, the blue one are the first. As you can see, the debonding is even before in the control is the ultimate load, and you can see after the debonding how is behaving the beam in the regular way, but how with the anchors the ultimate load and even the deflection is improved considerably. And the last plot, the lower one, is the difference between 3 layers of low density and on 1 layer of medium density, which is the same amount of steel. And in this case, as we thought before the test, the deflection is bigger because I told before the penetration of the mortar in the fabric is better. So finally, the debonding is later than in the other case. And as conclusion, this TRN textile reinforced mortar is effective for strengthening 1/3 scale RC beams of low performance concrete we defined in the beginning of the presentations. This debonding I explained depends on the concrete matrix shear strength. It's a point to study better. But this bonding was easily overcome with the use of U-shape anchors, which were not very difficult to install. And both systems they achieved the failure of the TRN, but the U-shapes present better behavior and are easier and cheaper to install. That is very important. And the future works should use different textile, and immediate action are to analyze the effect of this analytically or numerically, the effect of this TRM, even in full-scale beams of 4.5 meters, and to study the behavior of interface concrete TRM. That is we are working now. As you can see in the left upper picture, this is the bond test between concrete and this TRM material. In the upper right, the 4.5 span beam I told. We have tested some of them. We are planning to test more. And the lower picture are numerical simulation and also the analytical study with some regulations like FIB or Eurocode, and more or less the comparison between the analytical data and the experimental data. And thank you for your attention.
Bello, thank you very much as well. You referred to one of the keynotes, and it reminds me that your work can be compared with the first aid when somebody has a break in a bone of an arm or a leg, and so you make a very, very positive service. Thank you. We go to our next paper, which has the title Design of Prefabricated Multi-Layer Panels Manufactured with 100% Recycled Aggregates and Recovered LDPE, a paper made by 3 colleagues and will be presented by our colleague Garcia. The floor is yours.
Thank you, Mr. Chairman. Okay, my name is David Garcia. I'm going to present you a summary of a project developed in Tecnalia, a technological center from the Basque Country. This project was related with the recycling and valorization of some construction and demolition waste materials, and the intention was to use these materials to create new constructive elements, mainly focused on the recycled aggregates and the recycled low-density polyethylene. So I will start my presentation with a quick introduction to the construction and demolition waste, CDW materials. I will continue with a view of the possible options to recycle stony aggregates and low-density polyethylene, LDPE. I will continue with the design and presentation of some results about some concretes made with those 2 materials. And finally, I will present you some developments combining those concretes in the sense of create a multi-layer panel as the used for facades and other elements. So, all we know that in the construction sector we generate a lot of waste materials during the construction, renovation and the demolition of buildings and other structures. These materials are concrete, steel, glass and so on. So the intention in the last years is to, the first one of course is try to reduce the production of those materials in the workplaces, but also try to recover them as much as possible and use it in another process. So as I said before, I will focus in the recycling and the recovering of the stony aggregates to be used as new aggregates for concrete, and the recycled low-density polyethylene that is also one of the main waste materials in construction. Okay, looking at this figure here, we can see that concrete, mixed aggregates and ceramics are the main components of this mixed stony waste. At present they are used for some applications, but not related with structural works. For example, in roads and something like this. The current standards in some European countries allow to use some percentages of those materials in structural concrete. For example, in the case of Spanish structural concrete code, we can use a 20%, a maximum 20% of the coarse fraction over 4 millimeters to develop structural concretes, but we cannot use the fine aggregates for structural applications because of the problems related with the high absorption and the impurities present on those materials. So regarding the treatment process, as has been presented this morning, we have to wash to eliminate all the impurities, to select and separate the impurities and some low-weight components using modern techniques as artificial vision and infrared sensors, and then we need to crush and screen those stony aggregates to get a convenient aggregate. In the figure of the bottom, we have here the pink line represents the particle size distribution of the obtained aggregate, but we need to optimize this figure in order to place it just in the middle of the upper and lower limits stated in the current codes. Regarding the low density polyethylene, this plastic represents one of the main percentages in the plastic waste. So we can find, for example, this plastic in the wrappings, envelopes, and bags used to transport and to wrap other construction materials. So they are also present in the construction waste. And when we get this material, it has a high degree of contamination caused by land, dust, and so on. So the first stage, after first cutting in small pieces, consists on a set of operations of washing and drying these materials previously to other recycling processes. So, for example, in our project, we try to use directly this material with any other previous process, but the extrusion and other processes became very unstable. So we decided to do 2 sets of washing and drying cycles, and then we get the extrusion and cooling to get the pellets of the recovered low-density polyethylene. Okay, with these 2 materials, the recycled aggregate and the recycled low-density polyethylene, we design 2 different cement-based matrices in order to have a sandwich panel with 2 external leaves with some good mechanical properties, and an internal core made with more porous material. Here I put a table just to present some of the test campaign. We made a lot of combinations considering the different ratios between cement and water, cement and aggregates, with the intention of find a good balance between the workability in the fresh state of these microconcretes and the final mechanical properties, mainly the flexural and compressive strength. Here we have some pictures of the process, mixing of the materials, also testing the workability and mechanical properties at the lab, and also checking the distribution of the cement paste, the aggregates, and the LDPE elements. Sorry. Okay, after this process, we select two main dosifications, and we decided to cast some prototype panels. We use metallic mold with 600 by 600 millimeters, and the casting process consists of 3 steps. The first layer of concrete with the recycled aggregates. After this layer, the intermediate core with the recovered plastic concrete, and after that the final layer. With these panels, we perform several tests, not just to test the mechanical capacity, but also trying to get some information to compare sorry, this solution with available solutions in the market regarding the acoustic and the thermal isolation. So for the case of the acoustic isolation, we placed these prototypes in acoustic testing rooms designed for this kind of test, and we get an acoustic isolation capacity a little bit better than the standard concrete. So, for example, with these panels can be used directly when the noise level is the most common one. For example, with the normal traffic roads or something like this. In the case we are in a noisier area, like for example airports or noisy roads, we need to add some additional layers. For example, the laminated gypsums, as in other solutions. Regarding the thermal properties, we also test the thermal conductivity, and we compare them with two extreme materials, with the conventional concrete and also with the current solution for isolation, as for example the laminated gypsum of the polyester. We found that these panels have an average thermal isolation three times higher than conventional concrete. Okay, this can be understood as a good output, but if we compare this thermal conductivity with the real isolation materials, we realize that is not enough. Okay, also with these prototypes, we tested using the standards for glass reinforced concrete panels as reference, using a bending load. Here we have the flexural strength values obtained, and also they are compared with the conventional concrete. We found that the flexural strength values are between 2 and 3 times lower than conventional concrete. But we have to consider that this flexural strength is enough to support the self-weight and the wind force that are the main actions in this panel. And in any case, we are getting a much lighter panel. Okay, so now I go directly to the conclusions. We can conclude that the developed prototypes show a similar acoustic isolation to the solid concrete panels for the same panel thickness. However, we get a weight reduction about 30%, which means that the installation and the transport of these panels is easier and cheaper. With this work, we demonstrate the feasibility of use these recovered materials with only cement as the main origin material to develop new constructive elements. The idea is to continue this work, emphasizing the reduction of the energy used in the processes, because at this moment is too high to be economical competitive. And I would like to finish my presentation presenting our acknowledge about to the regional government of Biscay for the financial contribution to this project around tech. And I would like to thank you for your attention, and I'm ready for questions.
Thank you very much as well. Recycling is a very important item also in the development towards a sustainable world and sustainable housing. And I would like to ask, is one of the speakers arrived who was not here previously? Obviously not, so we are just on the half, but we started already very late. We come to our 6th paper. This is the number 130, a paper which is produced by 6 colleagues, and it will be presented by Mrs. Estokova, number 130, under the title "The Investigation of Resistibility of Cement Composites Against Biological Activity." We are looking forward.
Thank you. Ladies and gentlemen, I would like to present the part of our results in field of biocorrosion of building materials. So the term biocorrosion means the process of degradation of building materials which decrease the value of materials and construction. This process is caused by microorganisms and may result in total damage of material. We are interested in cement composites and concrete biocorrosion investigation. So in these processes, the very important role play mainly the sulfur oxidizing bacteria and sulfate reducing bacteria. So the sulfate reducing bacteria produce the hydrogen sulfide, which is in presence of sulfur oxidizing bacteria oxidized to sulfuric acid, which attack the cement matrix and react with the calcium compounds. And this process is very negative in point of view of building materials resistance and durability. So our laboratory experiments proceed by simultaneous effect of sulfate reducing as well as sulfur oxidizing bacteria in laboratory reactor during 90 days at constant temperature of 25 degrees of Celsius. We used many samples, many types of samples, but today I would like to present the results of investigation of two types of samples. The first one were the cement composite samples with 5% addition of black coal fly ash as cement replacement, and the other one were the reference samples without coal fly ash addition. The more detailed information about chemical composition of coal fly ash as well as preparation of samples as well as arrangement of laboratory equipment is or are in proceeding, in conference proceeding. We used both sulfate reducing as well as sulfur oxidizing bacteria. Sulfate reducing bacteria genera desulfovibrio originated from the potable mineral water Gajdovka from Slovakia, and sulfur oxidizing bacteria genera acidity oxidants originated from the mine water from the locality Smolnik, also from Slovakia. We were investigated surface changes, we were measured roughness measurements, we were carried out elemental EDX analysis, so the weight changes were measured as well as pH changes of leachates. So after 90 days exposition to both sulfur oxidizing and sulfate reducing bacteria, the surface changes has been observed, as we can see seen in the pictures. And also the new precipitated compounds were detected on the surface, probably as a result of reaction between calcium compounds and sulfuric acid. In these pictures there are some photos or micro photos from scanning electron microscopy, and the gypsum and ettringite was detected by elemental analysis. Also, the significant changes of roughness have been observed. As we can see in the pictures, the more significant changes were detected in case of reference sample in comparison to the sample with 5% coal fly ash addition. We have observed also the weight changes, and the weight changes were, in this case, decreasing of concrete samples weight. This results from the releasing of calcium compounds from cement matrix. Also, the pH changes of leachates were moved into alkalic region from 7.42 to 10.24. As conclusions, the biodegradation or biodeterioration process was manifested by surface changes as well as weight changes of samples as well as pH changes of leachates. The presence of gypsum and ettringite was confirmed, and the samples with 5% coal fly ash addition seem to be more resistant to the biological attack, but for more serious conclusion, the more detailed investigation is still in progress. Thank you for your attention.
Thank you very much as well. You reached the record in quickness. Yeah, thank you very much. So, ladies and gentlemen, we have some time for the discussion, and I would like to suggest to you the philosophy not to make too long comments and too long formulated questions, and don't keep to one of the speakers, but leave the possibility that everybody gets his or her turn. To whom may I give the word for a question or a comment? It's not the time for siesta. We had the lunch already long ago. Don't sleep, please. No, I forgot something to say. I forgot a compliment to make for the wonderful list what we got from the Hungarian colleague about the overview about all these insulation materials. It was really a wonderful overview. Thank you very much once more. Oh, well, the chairperson always has to have a question, of course, because I got already in advance a present about graffiti, but graffiti from centuries ago, wall paintings from centuries ago. I have to tell this, of course. Thank you very much. So I have to earn the present. Is the author of the first paper still here, the paper 116? Or is left? Oh, and the author of the Earth Houses? The Earth is, oh yeah. 123, yes. You told a lot about the qualifications of these mud and earth walls, and my additional question would be, how is this related also to the dimensions of these earth structures?
In our laboratory, we prepared a lot of different samples with different sizes according to the Union ISO norm, in order to measure in particular the hydrothermal properties of this material. We are not considering the strength properties of this material now, and probably I think that there is a further research in the future. So we concentrated at the beginning in earthen material like plaster and mortars, and we are carrying on this type of research in order to study the hydrothermal behavior of the building realized with this material, and in order to compare this material with the traditional material like fine clay bricks or concrete wall, because from different studies and from different researches we have the possibility to see that it's possible to achieve a better comfort door condition about the relative humidity value, temperature, and so on. In particular, when you are taking into account humidity and altitude climate sites like south region of the world. So this is the reason why we are not considering now the strength characteristics and so on.
I see. Thank you. Are you a little bit stimulated in the meanwhile to have more comments and questions in the audience to the other speakers? Well, it's not possible to force you. Maybe you earned the coffee break. So once more, an applause for all the speakers who of course were not always dealing directly with the housing questions, but with all these factors which are finally important for the quality for housing as well, in all these detailed material, methods and construction questions. So thank you very much for participating in this topic, and see you later.
presentation gets.
Oh, yeah, yeah, thank you.
If you want more information, so
Yeah.
you can get in touch.